I want you to just picture the internet in, say, January 2026, and specifically the kind of infrastructure you'd need to support 800 million active users.
That is the number OpenAI is dealing with. And to give you a sense of the speed here, the load on their databases, it didn't just double, it went up 10 times in 1 year.
Exactly. Now, if I were to design a system for that, nearly a billion users, 10x growth, the standard engineering playbook is pretty clear.
Oh yeah, you're immediately talking distributed systems.
Yeah.
Sharding.
You're talking about splitting data across hundreds of servers. You'd probably pitch some fancy proprietary NoSQL database that promises, infinite scale.
Right. The assumption is that once you hit that hyperscale level, the boring standard tools, the SQL databases we all grew up with, they stop working.
Right.
The physics of it shouldn't hold up.
But, and this is why we are doing this deep dive, that assumption is just wrong. We're looking at a technical post from OpenAI's engineering team by Bohan Zhang. It's called Scaling PostgreSQL to Power 800 Million ChatGPT Users.
And that headline alone is just, it sounds like a typo, doesn't it?
It's baffling. They are running all of this global traffic on PostgreSQL with a single primary writer.
One single database instance handling all the right traffic for one of the biggest applications on the planet.
It sounds like a ticking time bomb. So our mission today is to figure out how this thing doesn't just explode. We're going to get into the specific engineering tactics, from query hygiene to connection pooling, that let this standard database punch so far above its weight.
And I think the real theme here isn't magic, it's just rigor. It's about understanding the deep mechanics of the database so well that you can work around its limits. Because, as we'll see, the cracks were definitely starting to show.
Oh, massive cracks. So let's start with the basic architecture. You said a single primary writer. This isn't just one server sitting in a closet, I assume.
No. It's a centralized setup on Azure. They have one very, very large primary Azure or PostgreSQL flexible server. That's the node that handles all the writes.
So every prompt, every safe chat, every settings update, it all goes through that one single point.
Every single one. The blast radius for a failure there is, well, it's the entire user base.
That's terrifying.
It is high stakes. But for reads, and reads are the vast majority of the traffic they have scaled out, they have nearly 50 red replicas spread out all over the world.
Okay, so if you're just scrolling through your chat history, you're hitting a local copy.
Exactly.
So one writer, 50 readers. That sounds pretty standard for a smaller company. But at 800 million users, you must hit some fundamental walls in Postgres itself. The source post talks a lot about MVCC.
It is the absolute root cause of their biggest headaches. MVCC stands for multi-version concurrency control. It's basically how Postgres lets you read data while someone else is writing it without you two locking each other out.
Right, so I can read a row, you can update it, and we don't block each other. Sounds good.
It is, but it's the how that causes the pain. When you update a row in Postgres, say you just change a single timestamp, Postgres doesn't just change those few bytes, it copies the entire row to create a new version.
Wait, hold on. So if I have a user table with like a big JSON blob of settings and a bio, and all I do is update the last login timestamp.
It copies everything. The JSON, the bio, all of it gets duplicated. The old row becomes what's called a dead tuple. It's still on the disk, taking up space, but it's invisible.
So that's write amplification. You think you're writing 8 bytes, but you're actually writing, 4 kilobytes of duplicated data.
Precisely. And at their scale, doing that millions of times a second just fills the disk with bloat. And then your database isn't just serving queries, it's also wading through gigabytes of dead data just to find the live stuff. It kills your read performance too.
And the article describes this vicious cycle of outages they were having. It usually started with something totally unrelated, right?
Yeah, it was rarely the database's fault at the start. So a typical incident would be like an upstream cache node fails.
Yeah.
All of a sudden, the application can't find its data in the cache.
So it goes to the database.
And the database gets hit with a huge spike in traffic. Latency climbs. A query that took 10 milliseconds now takes 500. Then the application servers, they time out, they give up.
And then they retry.
And that's the killer, the retry storm. Now you have the original request plus all the retries hammering this already struggling database. CPU hits 100% and the whole service just goes down.
So I have to play devil's advocate here. I'm looking at this whole setup, single writer, write amplification, retry storms, and I just have to ask, why on earth didn't they just shard?
It's the standard playbook, right?
It's the first thing you do, just split the users up. A through M on this server, N through Z on that one. Why stick with the monolith?
It's a totally fair question, and Bohan is very direct about it in the post. Sharding is just incredibly expensive, not in money, but in engineering complexity and time.
Because you have to rewrite the entire application.
Everything. Hundreds of different endpoints have to be taught which shard to look at. You have to figure out cross-shard transactions.
Yeah.
You have to migrate petabytes of data without any downtime.
It's a multi-year project.
And in the AI race, you just don't have multiple years.
Yeah.
So they made a really pragmatic decision. They said, okay, we are not going to shard the monolith yet, but we are going to stop making it any bigger.
The no new tables rule, I found that part fascinating from a cultural standpoint.
It forces discipline.
Right. Imagine you're a dev at OpenAI, you've got this great new feature idea, and the infra team just says, cool, but you can't put it in the main database.
Exactly. They effectively froze the schema.
Well,
If you have a new workload, you have to put it somewhere else in a sharded system, like Azure Cosmos DB from the very beginning.
so they're triaging. The monolith handles the core ChatGPT data, but all the new write-heavy stuff gets sent somewhere else.
Yep. They optimized the monolith for what it's good at reads and diverted the problem workloads. And that bought them the time they needed to really optimize what was left.
Which brings us to the tactical optimizations. This is where we get into the weeds, because this wasn't just about changing a few settings.
No, this is a master class in database hygiene. And it all starts with the queries themselves.
There's a horror story in the article about a 12-table join. I actually cringed when I read that.
It's such a classic anti-pattern. They found a query running in production that was joining 12 different tables.
12? How does that even get through code review? Was it just select from the entire company?
Well, see, that's the thing. Nobody wrote that SQL by hand. It was generated by an ORM, an object relational mapper.
Ah, the silent killer.
Exactly. They're great for developer speed. You just write Python code and it generates the SQL. But a developer writes something that looks simple, like user.groups.permissions.history.
And the ORM generates a monster query that tries to stitch the whole database together.
And this one query was causing high-severity incidents all by itself. So the fix was ruthless. They just banned complex joins in the database.
But you can't join the user and permissions tables anymore.
Nope. You fetch the user, then you make a second query to fetch the permissions, and you stitch them together in your application code.
It sounds less efficient, but you're moving the work off the single database CPU and onto your endlessly scalable application servers.
So that's the logic. They also got really strict about killing idle queries. If a query is just sitting inside a transaction doing nothing, it holds locks and prevents the database from cleaning up those dead tuples we talked about.
So they just cut them off?
Yep. They set a timeout. Idle in transaction session timeout. If you're idle for too long, you're gone.
Okay, so the queries are clean, but you still have the problem of 800 million users trying to connect. You had a physical limit on connections, right?
You do. This is about memory and operating system limits. The Azure Postgres instances have a hard cap of about 5,000 active connections.
Which is nothing at their scale.
It's a rounding error. And what's worse, just creating a new connection is expensive. There's a TCP handshake, SSL, authentication. They were seeing connection times of 50 milliseconds.
50 milliseconds just to say hello. That's an eternity in web terms.
It really is. So they deployed PgBouncer. It's a connection pooler. It's a proxy that sits between the app and the database and just keeps a big pool of connections open and ready to go.
Like a taxi stand. The cabs are already there with the engine running.
Perfect analogy. And the impact was huge. Connection time dropped from 50 milliseconds down to about 5 milliseconds.
With 10x improvement just from better plumbing.
And they took it a step further by isolating noisy neighbors. They realized not all traffic is equal. You have critical ChatGPT requests, but you also have like a low priority background job.
And you don't want that background job to take down the main product.
Correct. So they split the traffic into high priority and low priority pools. If some new experimental feature goes nuts and uses all its connections, it only takes itself down. The core product is fine.
That's really smart. Okay, let's go to another layer. Because even with all this, the database is still the ultimate bottleneck. The best way to scale a database is to just not talk to it. Caching. But they describe this specific failure mode with caching called the thundering herd, which is one of my favorite engineering terms.
It's so descriptive.
Yeah.
So OpenAI uses a ton of caching, Redis, and memcached. Most requests probably never even touch Postgres, but cache keys expire.
Right, so let's walk through it. A really popular piece of data, maybe the main config for GPT-4, it expires from the cache at exactly noon.
At 1 second past noon, the first user request comes in. It checks the cache, sees the data is missing, and says, okay, I'll go to the database to get it.
Normal.
But at this scale, it's not one request. It's 10,000 requests, all arriving in that same second.
Right.
They all check the cache. They all see it's empty. And they all rush to the database to get the exact same thing at the exact same time.
And the database just vaporizes.
Instantly. So to fix this, they implemented something called cache locking.
How does that work?
The very first request that sees the cache, grabs a lock on that key. It basically puts up a sign that says, I'm on it. Everyone else, just wait here.
So the other 9,999 requests, just wait.
They wait for a few milliseconds. That first request goes to the database, gets the data, puts it back in the cache, and then releases the lock. Then everyone else can just read from the newly populated cache.
So the database only ever sees one query instead of 10,000.
Exactly. It's a cross-board for your database. A very, very necessary one.
I want to get into some of the deeper Postgres nerdery now because the post mentioned a scaling challenge with replication that I think a lot of people wouldn't even think about. We said they have 50 replicas. Keeping them all in sync is a big job.
It's a huge job. This is all about the WAL, the write-ahead log.
Yeah.
Every single change on the primary database gets written to this log, and then that log is streamed out to all 50 replicas.
So the primary is just constantly shouting, update this row, delete that row, to everyone.
Yeah, but imagine having to shout the same instruction to 50 different people, one by one. The primary was spending a huge amount of its CPU and network bandwidth just pushing out these logs. Adding more read replicas was actually slowing down the writer.
That's such a weird paradox.
It is. So what they're working on now is called cascading replication.
Like a bucket brigade.
Exactly. The primary only sends the log to a few intermediate replicas, and then those replicas are responsible for passing it down the chain to all the others.
But that has to add lag, right? If I'm at the very end of the chain, I must be seeing data that's a bit older.
That is the trade-off. Your replication lag goes up. For something like your chat history, a half-second delay is probably fine. But it means the application has to be designed to handle that eventual consistency.
It seems like every solution just creates a new, slightly more manageable problem.
That is the absolute essence of systems engineering. There are no perfect solutions, there are only trade-offs.
Okay, let's talk about one last thing, operational safety. We mentioned the no new tables rule, but they have another one that sounds incredibly stressful, the 5-second rule for changing the database schema.
This is all about preventing lock pileups. If an engineer needs to, say, add a new column to a table, they set a hard timeout. If the database can't finish the change in 5 seconds, the whole operation is automatically killed.
5 seconds. I've seen database migrations take hours.
Because when you're changing a table structure, you need an exclusive lock. And while that lock is held, nobody else can read or write to that table. If you hold that lock for even 30 seconds on a service this big,
you get a traffic jam that backs up and causes a retry storm.
Exactly. So they just refuse to hold the lock. If it can't be done almost instantly, they don't do it.
So how on earth do they backfill data? If you add a column and need to populate it for 800 million users, you can't do that in 5 seconds.
They do it very, very slowly. They have scripts that will update just a few hundred rows, then sleep for a bit, then do another few hundred. The post says a single backfill might take a full week to finish.
A week?
It requires a huge amount of patience. But the alternative is trying to rush it and causing a major outage. They choose stability over speed every time.
Slow and steady. So after all this, looking at the scoreboard, how is this boring approach actually working out for them?
The results are pretty staggering, honestly.
Yeah.
They have low double-digit millisecond latency at the 99th percentile, which means for almost every user, the database feels instantaneous.
And what about uptime?
5 nines. 99.999%.
That's elite territory.
And maybe most importantly, they've had only one SEV0, one critical site-down PostgreSQL incident in the last 12 months.
And we have to mention that one exception, because it was the ChatGPT image gen launch, right? A true viral event.
Yeah. Their write traffic went up 10x in a single week. 100 million new users started generating images almost overnight. It just shattered all their capacity models.
That's a black swan event. I don't think any architecture gets through that without a scratch.
No. But the fact that they survived it at all and stabilized it on that same single primary Postgres instance, it just shows how much headroom all these optimizations had created.
So what's next? Are they going to stay on this single instance forever?
No, absolutely not. Bohan is clear that this runway is finite. They are actively looking at sharded Postgres and other distributed systems for the future. But the key thing, and I think this is the lesson for every engineer listening, is that they didn't start there.
Right. They didn't prematurely optimize or over-engineer from day one?
They squeezed every single drop of performance out of the boring technology first, and that bought them years to plan the big, complex sharding migration properly, instead of having to do it in a panic during an outage.
That really does feel like the main takeaway. We look at these giant tech companies and we assume they have some secret magical technology, but so often it's just incredibly disciplined, rigorous use of the same tools we all have access to.
It's refusing to be lazy. It's understanding the internals of your tools, like MVCC. It's setting hard limits and sticking to them, even when it's painful. That is what really scales.
So here's the question I want to leave you with. If OpenAI can serve 800 million users on a single primary database just by being obsessive about their queries and connections, what inefficiencies are hiding in your stack right now that you've been blaming on the technology?
That is a question worth a deep dive of its own.
Thanks for listening to this deep dive into OpenAI's infrastructure. We'll see you next time.